All right. Hi everyone. My name is John Allwine. Today I'm going to be talking to you about an open source project I developed called Stl Command. And it's a suite of command line tools for inspecting, manipulating, and generating STL files, which is the most common file format used in 3D printing. But before I get into the details of Stl Command, I wanted to tell a little bit of the backstory, why I developed it, what the goals of the project are. If you know anything about me, it's that I like to make stuff. And when I was younger, it was almost exclusively software. But I did things that had some connection to reality. So I made the board games that I played as a kid. I used math and physics to make things bounce around. I generated instructions and diagrams for tying knots in real life. In college, I learned about 3D and took my programs to the next level. That led to pretty soon out of college getting a job at DreamWorks Animation, where I was a visual effects artist. And I got into this program called the Effects Challenge, where they trained us for 6 months and brought us up to speed pretty quick on how to be an effects artist. And within 3 years, I had credits on 3 different movies. So here are some clips of effects that I worked on. I did this Ash and Haze from How to Train Your Dragon. Did these Electricity and Sparks in Megamind. And I did this fireworks display in Madagascar 3. Yeah, ask me all about it. But by far my favorite part of working at DreamWorks was the Effects Challenge, the training program that I got into originally. And it was cool because for 6 months they paid us to do nothing for them except learn how to be a visual effects artists. And they basically told us how to be artists using math and science. And that's what I was good at. I was good at coding. And they took people with different backgrounds. They took developers like me with some interest in graphics, and they took more art-focused people who went through some digital arts background, maybe a little bit of programming, but they put us all together into these classes where we learned coding, we learned animation, we learned lighting, we went on field trips to art and science museums, and it was a great time. And we had deadlines for these assignments that they would give us. They're often very vague, subjective sort of assignments. And DreamWorks was a Linux shop, so one of the classes was how to use a terminal. And the assignment was find a beautiful image and make it more beautiful. And the only tools you got to use was a suite of proprietary image manipulation tools, command line tools. So we took a class on how to use the terminal, showed us the basics, common commands, and then just kind of threw us in to that assignment. And we had to find the commands we wanted to use, figure out what we wanted to do. And so we all had our own creative inspirations that we applied, but at the same time we were learning something very technical. And so DreamWorks, they named a lot of their commands the suffix of the type that this command worked with, underscore, and then something to manipulate it or do something with that file. So they had raster images, which is their proprietary image format, and they had R underscore some name. And so we would say R underscore, hit tab a couple times, and see what commands we had available. And we would just look through the documentation for each of these commands and figure out how to make a beautiful image more beautiful. I don't have much to show from the Effects Challenge, but this picture is actually generated by a ray tracer that I developed in the program. And we composed our own image, but my beautiful image, which I don't know if I succeeded in making it more beautiful, was that jellyfish right there. But yeah, so I ended up leaving DreamWorks, and that was about 6 years ago. And I started experimenting with making real things. because of my graphics background, it was really easy to step into 3D printing, representing virtual things on the computer and bringing them to life. And I had all this knot stuff that I'd written, so I started there, and I made some pretty cool products. So here's some earrings. I made some other kind of jewelry, rings, pendants. This is a gear shifter on my car. Actually, it's not on my car anymore. It's wine stoppers. But I felt constrained. I had all this coding experience and graphics experience, but I didn't have much making experience in general. Like, I was missing this foundational knowledge on how to make things. Didn't even know really what tools to get, what fasteners to buy, what materials, common materials I had available to me. And then there are more advanced things, like the electronic side of things. I had no electronics experience, never used an Arduino or Raspberry Pi. And I found myself wishing for a program that was like the Effects Challenge, that was super accelerated and taught at a very high level, had assignments that were intended to teach you how to do these things. And I called it the Maker's Challenge, and it's been kind of my career goal since then to see this program come to be. And so I pitched the idea at a startup weekend here in Bozeman. No one cared about it. But I met Rich Harges of Next Frontier Capital, who is on the board at the Children's Museum, and he had just pledged some money to renovate a room in the basement called Steam Lab. And he convinced me to come on board and run the show there for a while. And so I got to learn about Arduino and electronics and use coding to teach kids how to get into code. We did things with 3D printing. I put these kits together for kids. So here we're going to assemble a potentiometer just out of some nuts and bolts. This is something I designed to teach some electronics. So you build this thing, you wire it up to an Arduino, and then you code up that Arduino, and then you use it to communicate with Minecraft. I developed a plugin to allow for that too. So I had a lot of time to experiment with these kinds of ideas and had fun learning about making random things. It got me up to speed with a lot of that stuff. At the same time, I started teaching at MSU. I wanted to see this training program come to be, and I had no teaching experience, so I taught computer graphics at MSU just to get a little bit of teaching under my belt. And then I left both of those because it didn't seem like the right fit for this program that I wanted to see. So I went back to contract development work and started a blog based on making things, Arduino, woodworking, 3D printing, CNC, coding. And I just documented my projects, kept learning about these things that I wanted to see in this program. So here's a jog wheel that I developed for Pocket NC's 5-axis CNC machine. This is a music project, Circle of Fifths, that's hooked up to an Arduino and can play MIDI, so music output. These both have won prizes in Constructables contests. This is my workbench, which I ripped off from the workbenches at Pocket NC, but I implemented the design in OpenJS CAD and made this little 3D widget so you could customize the different parameters and get a different workbench, and it would generate the cut list and material list that you needed to make your own workbench, customized for your space and needs. So then, yeah, so now we're pretty close to today, and just a couple months ago I signed on at Pocket NC to be their principal software engineer. So now I develop software that controls and simulates 5-axis CNC mills. And if things go according to plan, we'll at some point hopefully implement this kind of training program to new hires at Pocket NC. So we'll see what happens. So anyway, STL command, how does that fit into this? pretty soon after coming up with the idea, I was thinking back to the effects challenge and thinking of that find a beautiful image and make it more beautiful assignment, and how could I turn that assignment into something that was maker related. And so with 3D printing, STL files are super common, and the file format is actually fairly simple. So I started writing these tools that created STL files or told me information about the STL files, and the number of commands that I implemented has grown over the years. But I envisioned creating an assignment like design your workbench for this program, and you would be forced to use these command line tools to learn how to use the terminal, which is now a necessary skill if you want to use a Raspberry Pi or a BeagleBone. So yeah, we'll go over first, I guess, what is an STL file. There's two kinds actually. There's ASCII and binary. The ASCII ones are plain text. They're human readable, which makes them bigger, slower to parse. So they're actually less common than the binary version. Most software that exports STL will export a binary, which is more compact, and it's easy for a program to parse and generate. So STL command functions exclusively on binary STL files. So this is the format. So an STL file, binary STL file, has an 80-byte header. First 80 bytes of the file, and then the next 4 bytes are an unsigned integer that represents the number of triangles in that file. And then following that are 48-byte chunks for each triangle. And the first 3 floats represent the normal of that triangle, and then the next 12 floats are the 3 points that represent each triangle. So it's just a list of triangles. When used in 3D printing, ideally they represent a watertight manifold solid. And so now let's just dive into the terminal here. Yeah, let's see here. Oops. Bigger. How big do you want it?
Big.
How's that? Can you see this? All right, so we'll just, here, I've got GitHub up here. So you can go to GitHub. This is all the source code's online. This is all implemented in C++ or C. It started out as C, but I got sick of that, so it's C++. So you can just clone the repository. There's no dependencies. It's all standalone, so it should be pretty straightforward to build. It is in Debian, so you can, I think it's in Debian testing, so if you have a Docker image, or you can use apt-get to install STL command. So you can also do that, Ubuntu Bionic. But yeah, we'll just go through some of these commands. So there's 3 kinds of files, commands. There are generators, ones that just generate 3D models, so basic primitives like a cube, a sphere, a cylinder, cone, torus. And then STL threads, I'll talk a little bit more about that, but just it generates threads for standard bolts and stuff. I was experimenting with threading things with that. The wine stopper, actually, you saw it threaded onto a pre-made wine stopper. So I wrote STL threads so I could put those onto my knots. But then there's informational STL commands. STL header, we can inspect that 80-byte header at the top. You can also manipulate that. That 80-byte header can be any kind of information. So it's often just a quick little thing like this was generated with this piece of software. So you can look at that. You might also put some copyright information or something, but it can be anything. STL count just looks at that count byte, so it's super quick. It just looks at that and returns it. STL normals will look at that normal information of all your triangles and compare that to a calculated normal based on where your points actually are. So that's actually can be a pain point for STL files. Because that normal is there in addition to the actual 3 points that represent a triangle, there's potential for that normal to vary from what your actual normal is. So you can kind of explore that sort of information with this command. bbox, just get the bounding box of their whole model. STL convex will just tell you whether it's a convex shape or not. So if you shrink wrapped it, would it be the same shape? Stl Borders. So when you're 3D printing, you want it to be a manifold watertight model. And that just means that the surface of your 3D model is completely contained. Like this is made up of triangles, which are a infinitely thin thing. So you need to have an inside of your model and an outside. And so when there's a hole, if you have a triangle missing, you'll have border edges that don't have a pair. So like if you have 2 triangles next to each other, you'll have 2 edges, and that's not a border edge. But if you have a hole, these edges have no shared triangle, so they have one edge, like only one triangle has this edge. So they're called border edges. So if you count the border edges in your model, if that's greater than 0, it's not a watertight model. So that can be helpful for debugging issues like that. And then STL spreadsheet, it can just output your data into like your actual point and normal data into a spreadsheet, so it's easier to look at. I might also implement like an STL to STL command that converts it to the ASCII format. And then we have commands that can modify STL files, so they read it in and do something with it. So STL merge is pretty simple. Since these are just lists of triangles, concatenating them is super simple. You can just chunk them together. So this is a super fast command to just merge multiple models together. But if they like overlap, you'll need, that can cause issues in the algorithms that actually slice your model. So you want to combine those somehow using a more complex process, which can be done with STL Boolean. We'll actually compute intersections and remove the intersected parts and make just one big model. And then STL transform can apply transformations in any order, so any rotations, scales, translations. So let's just jump in here and experiment, just to show off what some of these do. If anyone has questions, does anyone have questions so far? Okay. So STL cube, we just, every one of these commands you can just do -H. It'll give you some information about the command line. So we can create a cube of any dimension there. If you don't supply any output, it just creates the unit cube. So now we can do STL view. This isn't actually an STL command. This is just an alias to open up Blender. But you can just open this thing up. You can see that the dimensions here are 1, 1, 1. So we can do STL sphere, same sort of thing. STL view sphere.stl. Diameter of 2, so it's a unit sphere, a unit radius. Let's see what's going to demo actually. So yeah, there's nothing here. We'll do STL cube, STL cone. If we view both of those, you can see they're on top of each other. So if we go in here close, you'll see like, there's geometry inside of both of these, which can cause issues if we just merge those together. But if we use STL Boolean, where we pass A is going to be cube.stl, B is going to be cone.stl, and the output is going to be out.stl. And by default, it will just try to union these two things together. We can now say out.stl. And now if we go inside here, There's no geometry on the inside. It's just one surface. And that's what you want to see when you 3D print something. Nice manifold mesh. Yeah, so then we can inspect that file. We can make this a little smaller. So Stl Header of cube.stl. So in that 80 bytes, there's just this string, cube of width 1. Okay, that was put in there. Stl Header cone.stl. And if you download things off of like Thingiverse or something like that, you'll see all kinds of messages in here, like made with Rhino or made with whatever CAD software. So you can get sometimes a glimpse as to how someone made something. And if you're designing software or designing models, you can stick your own little copyright information in there using Stl Header as well. So we can do Stl Header -s copyright. Let's do quotes. Right, Allwine -o cube with header cube.stl. And so now Stl Header of cube with header will show that message. Do Stl normals. I just run that on cube. It says the normals match. So what does that mean? That means, so each triangle has a stored normal. That's the direction that represents the outside of the model. So because, like, you need to know what side is the outside or the inside of each triangle. And so that normal is what determines that. But not all software use that normal. Some people ignore that completely, or some software ignores that. And bases it entirely on how the points were oriented or laid out, like the order they were specified. The most common rule is to use the right-hand rule. If you curl your fingers around in the order that the points were listed, your thumb points in the direction of that normal. So some software follows that convention and just ignores the stored normal there. But if you have a model where they actually had a normal that was a useful information and the winding was in a reverse order, you can have problems with other pieces of software. So you can inspect that information, and it will tell you by default, it'll just say your normals differ from what the actual point, that right-hand rule ordering is. And then you can fix it. So you can pass command line flags that say, okay, just ignore whatever's in there and calculate it based on the ordering, or reverse the winding of your vertices, or look at the normal and make sure the points are in the correct order so that they would match. So that can fix some models. What else do we got here? Or any of these, does anyone want to see any of these commands?
Yeah.
Which ones? Pick one, come on.
Shows
The what?
Stl borders.
Borders, okay. So if all things are right, Stl Borders will show 0. I will show you where this does not actually happen. So all of these should be 0 right now. So Stl Borders, Q, or out.stl. So that out.stl, that was a output with Stl Boolean. Stl Boolean was one of my latest commands that I implemented, and it works for simple operations, like you do that cone and that cube. But if you start like doing operation after operation, so let's see, if I do Stl, let's move our sphere, Stl transform. So let's move our sphere.stl. Do I have one of those? No. Stl sphere sphere.stl. And then Stl transform. I'm going to transform that sphere over 1 unit. and then so sphere2.stl, sphere.stl into sphere2.stl. And the STL view out.stl with sphere.stl. Let's just look. So, oh, I meant sphere2. Okay, so now I'm going to subtract this sphere out of it. STL boolean A out.stl B sphere.stl dash D will do the difference into out2.stl. Yes, thank you. All right, STL view out2.stl. All right, so that did what we wanted to, but now let's see STL Borders out2.stl. Okay, that one's still okay, so let's do another operation. STL torus.stl. And we'll transform it -1 in x. So torus.stl to torus2.stl. STL view out2.stl and torus2.stl. Okay, and we'll subtract that out. If this doesn't work, I'll just show you. I know of one thing that definitely doesn't work, but so out2.stl, torus2.stl, difference into blah.stl. Okay, that's kind of what we expected, right? STL Borders, blah.stl. Ooh, 3. Okay, so the way STL Boolean works is it, like every triangle slices through the entire model. Well, not every single one, but it takes a model and it creates a binary space partition where it starts slicing the model up based on arbitrary planes it finds in the model. And it will keep splitting them until it has this tree all built out. And then you do that for multiple models, and then it's able to very quickly recombine them and only keep the pieces you want. But when you slice things up that small, you have only a finite precision with, it does it with double floating point precision, but eventually your triangles get so small that they become degenerate, or they're just so tiny you can't compute accurately. And so every once in a while you're left with these holes that are so tiny that they're hard to deal with. There are things that I'd like to implement to improve that, but for now, if you're doing enough operations, you'll eventually start getting these little errors. And there are ways to fix that. But I told you about my, let's see, I think we have 2 minutes left. No, we have 15 minutes left. Okay. I told you about my workbench, and that one of the assignments would be to design your own workbench using these tools. So I went ahead and did that for this presentation. So let's see. I think it's just called STL Workbench. So workbench.stl. Nope. All right, hold on. Not quite presentation ready, I guess. Just some live fixing of a bash script that's 300 lines, don't worry. There we go, okay, that one's taking a while. And the reason it's taking a while is because bash has no mechanism for doing floating point math. So every single computation in there was shelling out to a different command. And then every single temp file, like every command outputs a temp file. So let's just look at what that is. STL view, workbench.stl. So there it is. That kind of looks like what was in the widget. And we can do STL workbench. We can change the width. Let's make it a 4-foot bench instead of an 8-foot bench. And let's make it 30 inches tall instead of standing height. Let's turn the backboard off so it's just a table. And then we'll output that into table.stl. And there we go. We've got a 30-inch table, 4 feet wide, 3 feet deep. So, does anyone want to see what that script does? Alright, so it's just a bash script. Define some variables here, and then read in some flags to overwrite some of those variables. And then a bunch of calculations here. It gets hideous. So this is how you do calculations in bash. So this backtick thing here, we are creating this string that we're just going to echo. So the echo command just prints it out to the terminal. So we're going to create these variables, stick them into a string, echo that, and then pipe the output of that into this VC command, which then evaluates that and returns another string. So that's why it's so slow. Every one of these calculations is done in a separate process. But then we have these functions here that initialize a bunch of temp files, because every command has to go out to an output of some kind. And so we create a cylinder. This one's going to define a 2x4 with chamfered edges. So these cylinders represent the corners, so it's a rounded edge. But instead of rounded, I made them 4-sided, so it's just a chamfer. So I can show you what this does. That's why I was commenting this all out. Let's comment this out and just look at that 2x4. Oops. So vertical 2x4, 10 inches tall. So STL workbench into 2x4. Okay, and so we have a 10-inch 2x4 here with chamfered edges. Let's round these edges instead of chamfering them. So the STL cylinder command here has this -s option where you can specify how many segments to approximate a cylinder. So that's set to 4, so instead of a cylinder, it's actually just a rectangular solid. So let's make this like 16. So there's 4 corners, so I'm changing it. We'll run this again. And there, now we have a pretty nicely rounded edge instead of a chamfer. You guys have any questions? Anything else you want to see from these commands? We've got about 10 more minutes. I could keep going through this program. Is anyone going to try to use these tools? What's that? Blender's free, yeah, you can download that for free. Yeah, okay, let me show you that. So STL View is not a command that I implemented. It's something I'd like to do, but whenever you have a viewer of some kind, it introduces some kind of dependency on a graphics library. And I didn't want to do that. So STL View is actually the alias around Blender, right there. So I just start up Blender and I run this Python script that loads any STL files that you have on your command line. And that's all up on GitHub too. Yeah? The widget? Yeah, that was all implemented in OpenJSCat. That's a JavaScript library. I actually gave a talk on that last year, but I'm happy to answer any questions on that. Yeah, grab me after it and we can talk about it. Anything else? Do you want me to just bumble through this script? You want to learn anything else about Bash? Okay. At DreamWorks, we actually use C Shell, so this was a learning experience for me as well. But they're similar. What's that? I have not tested it. I imagine there's definitely not a port of this script, but I imagine you could get the source code compiled on Windows and pretty easily convert this over. I have no experience writing shell scripts in Windows. But yeah, there's no dependencies on STL commands, so it should be pretty straightforward for it to get it to compile. You could probably use SIGWin or MinGW as the compiler. What's that? Yeah, so I mean, if you want to go that route, you certainly could do that. That one would definitely happen. But yeah, so Bash, the functions in Bash are, you can't even return anything other than an integer. So these functions are all, I mean, I could actually take them out and make them not functions. At the end, you see I always cat the file out just so that I can then capture the output of the function. So I call left front leg, cat that out to a file, or redirect it out to a file. So yeah, I don't know, do you guys want to know about like pipes and redirects? How familiar are you with the terminal? Okay, so these on all of these functions shell out to this other command called make temp. So this is just creating a blank file on the file system, and make temp will fill in these X's with a unique name. So every time you run the program, it will generate a unique file. I end up deleting all of those files anyway, but if you're running the script multiple times, like at the same time, you're not going to be stepping on each other's temp files. So that's what I'm doing here. But yeah, whenever a program sends data to standard out, you can just use this redirect to dump that output into a file. So that's what I'm doing with all these angle brackets. If you want to take the output and pipe it to a new process, and that new process will take that as standard in, you can use a pipe. So that's what these pipes are. Yeah, and then Bash has weird equality checking. It doesn't have any floating point arithmetic. It can compare strings and integers. So even just my comparisons, like is this variable greater than 0, has to shell out to another program just to check that. So this isn't the ideal way to 3D model. The idea is that if you want to learn the terminal and you're in the 3D printing space, you might use it as a learning experience.
With all of the annoyances of Bash shell, like without the floating points, is there a reason you chose that over just writing the whole thing in C and then just taking the arguments? Or how about Python? Or Python?
So you could certainly use Python and shell out to these commands. The goal of STL command in general, though, was just to force you to use a terminal. So you don't have to write a script. There's no real point in using it to write a script. But if you want to quickly look at a file, like that's handy. I'll do that all the time. I'll bust open a terminal and just see if it has any border edges, see if I can 3D print this, see what they use to generate it. So look at the header in there. So you can quickly do something, and so the overall goal was not to use a script like this in any kind of production environment or in any kind of pipeline that you would want to be really efficient. It's more just a way to get makers who aren't traditionally necessarily programmers and who are probably unfamiliar with the terminal, to get them more familiar with the terminal by giving them a task that they are somewhat familiar with.
Walk through like the logic of those crossbeams on the side, just kind of where you go through that in the script
Sure. Yeah, so I created this function 45 2x4. So I have some temp files there. So I just call the vertical 2x4, put that into a file, transform it, so I rotate it by -45 degrees. And then create a cube so the 2x4 has been rotated, so now a cube that's unrotated will be able to slice off those corners, and it takes the function takes some parameters. So here, let's look at the workbench really quick. So there are these cross beams that have 2 45 cuts. So one there, one at the bottom. And then there's these 45s up here where it has 1 45 cut. So you can pass in whether you want 2 cuts or 1. So if you want 1 cut, it'll just do this one. If you want 2 cuts, it will put two cubes to make those 2 45 cuts. And then there's some extra flags whether you want it rotated at 45 or you want to keep it straight and just have a 45 cut.
So you have to really think about the negative space almost for subtraction as much as...
Definitely, yeah. You got to think about, yeah. And so yeah, that's another thing that's kind of tricky. Like if you're doing this in code or in the terminal, like you have to think a lot more about the equations and like where to position things. Whereas in CAD, you basically just like click an edge, click another edge, and it will do the math to like make sure that those things align, or a face to a face, something like that.
So correcting the issues that you were talking about, you command that, would you be able to do that in some fairly?
I do not currently. I would like to implement some of those. So like STL view, right now it's an alias to open up Blender. I would like to implement STL view as a native app that can show you some of those problems. I used to use NetFab Basic, which is a free piece of software. It was acquired by Autodesk. It no longer works on Macs, so I don't have a good way of showing how to fix those problems. I do have a command line tool that can kind of brute force it. I can show you that as well. Actually, I mentioned that in the talk description. I forgot. So there's another suite of commands called VDB _command. And VDB is a sparse volume format. So instead of representing a solid as a mesh, like with just the surface of a model, you can represent it as in a voxel format. So you have a fixed number of points next to each other, and it's like, is this part of the solid? Yes, no. Is this part of the solid? So you have all this grid information to represent it. OpenVDB was developed by DreamWorks Animation, and they open sourced it about the year that I left. And it's called a sparse volume format, so it only stores data where there's actual information, like right around the surface of a model. So it's an efficient way to represent voxel data, and it's all open source. And there's an STL to VDB command. So let's see, Stl Borders workbench.st. So there are 36 problem areas in this, so holes in my model. I don't know where they are, but I'm going to STL to VDB. I'm going to rasterize this into a voxel format. So I'll set my voxel size to 0.1. Hopefully this will finish. I don't know if this will work. Into workbench.vdb. So it's converting it. It's pretty heavy. So this workbench is 10 feet long. So recording every 0.1 inches might be too heavy for it. Let's see how quickly my memory's going up into smoke. I don't see anything crazy. 300 megs. Complete, perfect, okay. VDB view, workbench.vdb. Okay, so now it has all these coordinates and you can turn off. I didn't implement this, comes with OpenVDB. So there's my workbench as a solid. So it successfully rasterized it into this volume format, even though there were holes in it. And now we can convert it back, STL or VDB to STL to workbench.vdb to out.stl. So now it's going to remesh it. So it turned it from a solid to back to a mesh. And it's going to be a much denser mesh, so like the output of this, so if I look at the file size of workbench.stl, it's 102K. If I look at the file size of out.stl, it's 25 megs. So it's not the ideal way to fix things if you can fix it in a simpler way, but this can be a brute force method to fix a model. And now if I do Stl Borders on that out.stl, it's watertight. So if we look at this now in Blender, you'll see just how dense the mesh is. Yeah, so there's no reason to have information within this surface because it's just one big plane, but that's a side effect. So you could continue to process this to bring the file size down, but it's a good model now.
So this is essentially snap to your grid. Why not have your boolean function be able to snap to your grid object?
I mean, you need the precision of them colliding right wherever they actually collide for the map to work out. This isn't necessarily snapping to a grid. It just represents it in a much denser way. So yeah, I mean they're different algorithms. It's not going to work in a mesh-based sort of algorithm. Any other questions?